What's going on, everyone? Welcome back to another video for the AI for Aspiring Researchers lecture series. In this video, we're going to be going over PCA, which stands for Principal Component Analysis. And specifically, we're going to be using PCA for the Hazardous Asteroid classification, and this dataset was provided by Shruti Mehta and can be found on Kaggle, link below in the description. Awesome. So basically what PCA is, if you don't already know, is it's basically a way to kind of reduce the number of features that we are considering, right? So you might be given a problem that initially has X number of features, say like 100, and that takes a lot of time. The more features, the more time your algorithm requires to train a model. And so what dimensionality reduction does is it finds a way to kind of eliminate the unnecessary features and only consider the features that are actually useful, and so that we kind of reduce the number of features and thus increase the speed at which our algorithm trains a model. And so let's jump right into it. Right, so the first thing that we're going to be doing, as always, is import the required libraries. And so we're going to say import numpy as np, import pandas as pd, and then these are kind of like the unusual libraries as well, but very useful. So we're going to say s from sklearn, we're dot processing import standard scalar. Awesome. So then we're going to say from sklearn dot decomposition import PCA. Okay. Then we're also going to say from sklearn dot model selection import train test split. Now, if you don't already remember what train test split is, all it's doing is that it takes our dataset, splits it into a training and testing dataset, and we use a training dataset to train the model and the testing dataset to actually test how well the model worked or how well it actually learned stuff. And then we're also going to say from sklearn import our SVM. So if you haven't already seen the last video, I believe, we talked about SVM there, or support vector machines. And in this video, what we're really going to be doing with SVMs is just kind of to show how well our model worked whenever we applied PCA to it, or Principal Component Analysis. Okay, so let's go ahead and run that. And now what we're going to do is we're going to say df is equal to pd.read underscore CSV, and we're going to feed in our nasa.csv. So this is the data that holds all the features and all the values of each of these asteroids and whether or not they are hazardous. So I'll go ahead and print the head of that just to show you. Okay, so you can see here that essentially each of these rows represents a different asteroid, and each of these columns represents a different attribute or feature for these asteroids. And so you see the NEO reference ID, the name, the absolute magnitude, estimated diameter, I believe, and so on and so forth. And then this last column over here is whether or not it's actually hazardous. So true obviously means it is, and false means it is not hazardous. Okay, so what we basically need to do is we need to see how can we reduce these total number of features, because there are a significant number of features. So how can we figure out which features are actually kind of the most important ones and use a limited number of features in order to do so? Okay, so what we're going to do is, let's delete that. Now, before we do anything, the first thing that we really need to do is kind of cleanse this data. And so we need to reduce, or we automatically need to eliminate some of these things like NEO reference ID, name, and the reason for that is that typically these things won't really have an effect on whether or not it's hazardous. These are just kind of names associated or ID numbers associated with the asteroids arbitrarily. And so what we can do is we can automatically reduce those. And then also, for sake of simplicity, I decided we would also reduce like these dates, just because you'll see later on when we're dealing with numbers and scaling, it just becomes easier to just ignore these dates or timestamps, and also these like equinox where it's a letter and a number. And so what we're going to do first is we're just going to go ahead and cleanse this data. So we're going to say df is equal to df.drop. Now what this does is that it drops the columns that we feed in. So we're going to say columns is equal to, now first one is our NEO reference ID, then let me just actually copy paste all of these, name, then after that is going to be our close approach date, so this thing right here, and remember it's a date, so this is just for sake of simplicity that we're doing this. Then we're also going to say orbiting body, over orbiting body, which over here is Earth, so we're just going to go ahead, copy paste that. Next, we're also going to say orbit ID, which is right next to it, orbit ID, orbit determination date, and finally our equinox. Okay. And also another thing that we need to do is, you see over here in this last column how we have true, false, true, false, true, but instead of that what we want it to say is 1 0 1 0, right? So ones would represent true and zeros would represent false, and it's actually really easy to do that. All we have to say is df, and then we feed in our hazardous as our index for the column. We're going to say times equals 1. Now we're going to say df dot head. Okay. So as you can see, the data is now changed. We got rid of that neo-reference ID and name in the beginning and rid of all those other columns in between. And the last column over here, hazardous, now says 1 0 1 0 as opposed to true, false, true, and so on. Okay. So now the next thing that we actually need to do is gather these into an x and y. Right, so our x would essentially be all the values for all the asteroids, for all the columns with out or except this hazardous column. So it would just mean like this block right here all the way to the beginning, but this block right here without the hazardous all the way to the right. And that hazardous column, this entire column, is essentially going to be our y column. And so now in order to do that, all we have to say is x is equal to df dot I LOC, and then we're going to say all the rows, which is represented by this colon, all the rows, and then we're going to say 0 colon negative 1. And now what that's going to do is it's going to gather all the columns, or all the values in all the columns from this 0th index column to negative 1, which basically should be hazardous, but it's excluding, so only to here in all these values. So it's going to gather that block of values or data. Okay, then what we're going to say is also y is equal to df dot I LOC, and we're going to say the same thing, so colon, and then this time negative 1. And now what this is going to do is it's just going to gather all the values, which is represented by this colon, all the rows in this one column, in this hazardous column. Okay, now I want to show you exactly what happens with that. So you see this x. Okay, so when you print out x, you get these values, and you get all the values, so absolute magnitude, mean motion, all of them, but it's excluding this hazardous. And same thing if we were to do this with y, you would see the same thing, right? So this is just the hazardous column where you get 1 0 1 0, so on and so forth. Okay, awesome. So let's get rid of that for now. Now what we're going to do is we need to scale our data, right? Because over here you can see these numbers are significantly large, right? And so if we were to actually go ahead and train this on our model, one, it would, even if we wanted it to be efficient, it would take years to do so, but just because considering the size of these numbers, and two, it would not be that accurate, right? Because these numbers are so big and these numbers are so small, kind of changing everything would be very, very tedious, and so scaling it is of utmost importance. And so what we're going to do is we're going to say x is equal to standard scalar, and then we're just going to say fit transform and then x. So what this is basically doing is it's scaling all these values in this x data, right? So that's what we stored right here. And so what we're going to next do is just say print x. Okay, what is the issue? Oh, I see. This is there. Okay, awesome. So now you can essentially see that all these values are scaled down. So you see basically what this standard scalar is doing is it's taking these numbers and scaling them between -1 and 1 appropriately. And so you see all these values in this 2D array, right? So this first array in this 2D array is basically representing the first asteroid, and then so on and so forth until the last asteroid over here and all their attributes. Okay. So next what we're going to do is we're actually going to implement that PCA algorithm. And so what we're going to say is PCA is equal to PCA, right? And then we're going to go n components equal to 4. And the reason I'm doing 4 for now is that you can honestly choose any number of components between, I think, 1 and the total number of attributes there are. And so what n components 4 is doing is it's basically saying, okay, I have, I have all of these attributes right now, but now let's say I only want 4 attributes to describe whether or not this is hazardous, right? Rather than using, I think, 32 or 33, or just use 4, right? And so what we're going to do is say PCA is equal to PCA n components 4, and then next we're going to say x is equal to PCA dot fit underscore transform and then x. Now all that's doing is it's just going to create an array with all of our values for these new attributes and only 4 attributes. And so you'll see exactly what that does right here. Okay, so what this is doing, as you can see, is it's basically having now only 4 columns and the same number of rows really. So what you saw over here is that you have essentially 32 columns with all these different values, and so that's a lot of data that we're using. But now we cut that down significantly because we only have 4 columns, and PCA automatically takes care of how exactly it creates these numbers. And I won't go too much into detail, but if I'm not mistaken, basically what it's doing is it's taking the correlation between all of these different values or these different features, and then extracting them into said number of columns that we've inputted using some sort of formulation. Okay, now what we're going to do is, now that we have essentially the values for the componentized, I suppose, array, what we can do is we can actually change it into our training and testing, or we can actually split it into a training and testing data. And so what we can say is xtrain, xtest, and then we're going to say ytrain, ytest is equal to train test split, and we're just going to feed in our x, our y, and our test size, I guess, as usual, we'll just put as 0.2. So what this is saying once again is that 0.2 or 20% of the data that we have will go into our testing, x-test and y-test, and then the remainder will go for training. Okay. Then what we'll say is ytrain is equal to ytrain dot reshape 1, -1, and then 0. And so what this is essentially doing is, if you actually don't reshape it, and you actually pull the data directly, you're going to get a 2D array with multiple arrays of just one element being 1 or 0 or 1 or 0. And so what we're essentially doing here is we're kind of creating that and changing it into 1D array with just a list of 1s and 0s corresponding to whether, or to each asteroid, right? So we're going to say xtest dot reshape, and I'll just copy this over actually. Okay. Now what we're going to do is we're going to create that classification using our SVM. So we're going to say CLF is equal to SVM dot SVC. So once again, SVC just stands for support vector classification. And we're going to say kernel, as used last time, linear, and C is equal to 0.9. Okay. Alright, so essentially what we're doing here is we're creating this SVM for the classification, and we're going to be using this xtrain and ytrain to train this classification. And remember, this xtrain and ytrain is now getting split off this x and y. And so this x is this newly transformed, or using PCA. And so this is essentially the x that we're using for the xtrain and xtest. Right, and that's what these are the values that are going to be fed into our SVM in order for classification. Now what we're going to say is clf.fit and then xtrain and ytrain. Okay, now we'll go ahead and run that. This doesn't have attribute reshape. Why? Because it is a series. Okay, so Let's actually go ahead and do this. Let's just see what happens if we just run this. Okay, perfect. So what it's doing is it automatically kind of creates this classification. So I think what was going on over here is that, well, let's actually run this and I'll come back to that just to make sure. So what we'll say is score is equal to CLF dot score, and then we're going to pass in our X test and our Y test. Oops, Y test. Okay. And then we're going to say print score. Okay, awesome. So I think what was happening over here was initially when I first ran this to kind of test the code, make sure everything was working properly, I used, instead of a series, I created a separate data frame. And so because of that, it might have messed up a little bit. And so what you can do is, in order to fix that, I guess there's no need to even say this anymore, but I guess what you could do to fix that is just make sure you're using the right thing, because clearly I didn't, but make sure you're using like series, you know your methods for series and you know your methods for data frames. Okay, but yeah, basically, I guess ignoring that, what we're doing over here is now we're training the model, we're fitting it for SVM, or SVC I should say, and now we're gonna go ahead and actually score it on the testing data set. And so you see this over here, this X test and Y test, CLF.score, what it's doing is it's basically taking the model that we trained here and inputting now our testing data set into that model to see, well, how well did this model work? And we're now printing the score, which comes out to be about 0.84. So what this means is it's basically saying that 84% of the time we're correctly predicting whether or not the asteroid is hazardous. Now, you might be wondering, well, that's relatively low. Well, it's obviously a trade-off that we're making with PCA, where basically what we're saying is that we want to make our algorithms much faster by reducing the features, but this might come at the expense that we also reduce our accuracy. And so what you'll notice is that the as the n components increases, so as you increase the number of components over here, say if we were to go ahead and maybe put, instead of 4, let's say 15, right? And we were to run all, right? And so you'll see a much higher value, right? So you see 96%, because now instead of 4 features, we have 15 features. And you can keep doing this until 32, and we can try it. Let's go ahead, try it, see what comes out. You'll see 95, right? So actually, the 15 actually performed a little bit better. Right, and so this is kind of the things that you might want to train and you might want to test out, and I guess it just comes with more and more practice. You'll kind of figure out the number of components that will work best for you, and so over here it's 95, and the reason it's changing is because every time we run this SVM, it's like obviously it randomizes a little bit, and so it changes up some things, but these are obviously, the number of components is just a very variable thing, and that's kind of user dependent on whatever you want, right? And so I guess the main takeaway from this whole code is using PCA. The whole point of it, and dimensionality reduction, is the whole point of it is to take the number of features and reduce them so that we can make our algorithms much faster. And you'll see in many like real life scenarios, so in this case we're only considering say 32, or I think like 32 features. And for real life, I guess that's not really that many. But sometimes you'll see some things even go up to like millions of features, and that's ridiculous to train on a regular computer. And so PCA comes into real handy whenever you have these number of features, because what you're able to do is take all these features and essentially reduce them to a more manageable level, and still get relatively good amounts, or relatively high accuracy, as we saw, because even if we ran 4, and 84% is still not bad. And you can even go ahead and say do 5, 6, I won't do it now, but just obviously train and just kind of practice on, see how many components typically are good for a certain amount of problem, right? Or so, like if you say want a problem with really high accuracy, then maybe PCA won't be the best idea, because what you're doing is, because it's a trade-off, right? What you're doing is that you're saying that whenever you have less features, I'm also gonna say have the possibility of less of accuracy, right? So, but now let's say that you want a really fast algorithm as opposed to or a really fast algorithm is more important to you than accuracy, then PCA will come into really handy, right? And so once again, it's honestly just a trade-off and seeing which one best suits the problem, which one best suits you. And so go ahead, try it out, try different components, try a different data set, and just I guess see which ones work, how well which component number works for you, and yeah. Well, if you like this video, make sure to subscribe, like, feel free to leave a comment. Once again, as always, if you have any other questions, just comment below. I'd love to see your questions and love to answer them and hopefully make a new video on them. And I'll see you next time.